Hello, fellow Homo sapiens, and welcome this channel. Take a moment to settle in. Whether you're preparing to sleep, unwinding after a long day, or simply letting your mind wander while cooking, showering, or working with headphones on, this space is for you. Here we explore slow science and quiet storytelling. No hype, no noise, just careful history, humble archaeology, and thoughtful reflection told softly. If this kind of long-form content speaks to you, consider liking and subscribing. It helps others discover a calmer way to learn and grow curious. I'd also love to hear how you use these stories. Do you listen at night before sleep, or during the day while working? Have you ever considered that the very act of hearing these words might be fundamentally changing the nature of reality itself? That somewhere in the quantum realm beneath your fingertips, particles are shifting between existing and not existing based purely on whether you're paying attention. This isn't science fiction. This is quantum mechanics. And right now, it's presenting scientists with paradoxes so profound, so deeply unsettling that some of the world's brightest minds are questioning whether reality, as we understand it, even exists at all. Welcome to this quiet corner of the internet, where science meets contemplation, where the impossible becomes inevitable, and where the deepest mysteries of existence unfold in the most unexpected ways. I'm grateful you're here, settling in, perhaps with a warm cup of tea or finding a comfortable spot as the day winds down. Whether you're listening in the early hours of morning or the gentle fade of evening, you've arrived at the perfect moment to explore something that might just change how you see everything around you. Tonight, we're diving into quantum paradoxes that are keeping the world's most brilliant physicists awake at night. Not because they are difficult to understand, but because understanding them reveals something so fundamentally strange about the nature of existence that it challenges every assumption we've ever made about what it means to be real. But before we venture into these mind-bending territories, take a moment to notice where you are right now. Feel the weight of your body, the rhythm of your breathing, the simple fact of your presence in this moment. Hold on to that feeling because by the end of this journey, you might find yourself questioning whether any of it exists in quite the way you think it does. Picture this. You're standing in a laboratory looking at a machine that can split a single particle of light into two paths simultaneously. Not one path or the other, but both paths at exactly the same time. The particle, according to quantum mechanics, exists in what scientists call a superposition, taking both routes through the experiment until something extraordinary happens. The moment you decide to check which path the particle actually took, it suddenly inexplicably chooses one path and abandons the other. Not gradually, not through any physical force you can measure, but instantaneously, as if the very act of your observation reached back through time and forced the particle to make a decision it had been avoiding. This is the quantum measurement paradox, and it's driving physicists to what can only be described as an existential crisis. Because what this suggests in the most unsettling terms possible is that reality doesn't exist independently of observation, that the universe in some fundamental way requires witnesses to become real. Dr. Káclav Bruckner at the University of Vienna has spent years wrestling with this paradox, creating increasingly sophisticated experiments that push this weirdness to its absolute limits. In his extended version of what's known as Wigner's friend paradox, he's demonstrated something that should be impossible according to our everyday understanding of the world. Imagine two scientists, Alice and Bob, each working with quantum systems in isolated laboratories. Inside each lab, their assistants, let's call them the friends, perform measurements on quantum particles and record definite results. From the friends' perspective, they've measured something real and concrete. The particle was spinning up or it was spinning down. Simple. But here's where reality starts to fracture. When Alice and Bob look at their entire laboratory systems from the outside, including their friends and the quantum particles together, quantum mechanics tells us that everything inside, including the friends themselves, exists in a superposition. The friends are simultaneously in states of having measured spin up and spin down, even though each friend experienced only one definite outcome. Recent experiments have confirmed this impossible-seeming prediction. The correlations that Alice and Bob observe from outside the laboratories violate what should be fundamental limits if each friend truly experienced a single definite outcome. This isn't a failure of our measuring instruments or a limitation of our current technology. This is quantum mechanics telling us that there's something profoundly wrong with our basic assumptions about reality. The implications are staggering. Either quantum mechanics breaks down when applied to conscious observers, requiring entirely new physics we haven't discovered yet, or one of three cherished beliefs about the world must be abandoned forever. Either measurements don't have single definite outcomes, or we don't have the free will to choose our experimental settings, or information can somehow travel faster than light. Each option represents a fundamental assault on how we understand existence itself. The idea that measurements don't have definite outcomes suggests that reality is permanently ambiguous, existing only in probability clouds until observed. The possibility that we lack free will implies that our choices are predetermined by hidden variables we can't access. And faster-than-light information transfer would shatter our understanding of space and time. As you contemplate this, notice how it feels to consider that your own observations might be actively creating the reality you experience. What if the act of listening these words is literally bringing them into existence, and without your attention, they would remain suspended in quantum uncertainty? But the observer paradox is just the beginning of quantum mechanics' assault on reality. Perhaps even more disturbing is what happens when we scale these effects up from individual particles to entire systems to cats, and potentially to universes themselves. You've probably heard of Schrödinger's cat, the thought experiment where a cat in a box is simultaneously alive and dead until observed. What you might not know is that scientists have now created real-world versions of this paradox that persist for unprecedented lengths of time, bringing us face-to-face with the possibility that macroscopic objects, things we can see and touch, might genuinely exist in multiple contradictory states simultaneously. In recent breakthrough experiments, researchers have achieved what they call quantum cat states, lasting an incredible 23 minutes and 20 seconds. Not with a single particle, but with 10,000 ytterbium atoms, all existing in superposition together, all simultaneously spinning in two opposite directions at once. Let that settle in your mind for a moment. 10,000 atoms for nearly half an hour existing in a state that defies every intuition we have about how the world works. They weren't spinning clockwise or counterclockwise, they were spinning both ways at exactly the same time, creating a macroscopic quantum system that challenges the very notion of definite physical properties. These experiments represent a trillion-fold increase in the duration of macroscopic quantum superposition states. We're approaching a theoretical threshold where everyday objects might genuinely exist in contradictory states until observed. The boundary between the quantum world of possibilities and the classical world of definite outcomes isn't fixed. It's dissolving. What's particularly unsettling is that these quantum cat states don't just demonstrate superposition in a single location. Recent experiments have created what researchers call two-mode cat states, where a single quantum system exists in superposition across two completely separate physical locations simultaneously. The same system, the same atoms existing in two places at once until the moment someone decides to look. This progression from microscopic quantum effects to macroscopic quantum behaviors represents what can only be described as an erosion of the classical world's apparent solidity. The comfortable, predictable universe of definite objects with definite properties is revealing itself to be a thin veneer over a deeper reality of quantum possibilities and observer-dependent existence. Professor Wang, who led some of these groundbreaking experiments, puts it simply. It proves that our quantum technology has advanced to the point that we can make such a cat state with large numbers of particles of multiple varieties. But the implications extend far beyond technological achievement into deeply unsettling questions about the nature of reality itself. If macroscopic objects can exist in superposition states, what prevents you sitting there right now from existing in multiple contradictory states until observed? What makes your current experience feel singular and definite when the fundamental laws of physics suggest that everything at its deepest level exists as a cloud of possibilities? The answer, disturbingly, might be nothing at all. Some interpretations of quantum mechanics suggest that you're constantly existing in superposition, experiencing every possible version of this moment simultaneously with your consciousness, somehow selecting or creating the single thread of experience you perceive as reality. As if the measurement paradox and macroscopic superposition weren't strange enough, quantum mechanics presents us with another deeply disturbing phenomenon: the power of observation to literally freeze physical processes in time. This is known as the quantum Zeno effect, named after ancient Greek paradoxes, and it represents perhaps the most direct demonstration of how observation can exert controlling influence over physical reality. The quantum Zeno effect works like this. If you observe a quantum system frequently enough, you can prevent it from evolving naturally. The act of measurement repeated at regular intervals literally freezes the system in its current state, preventing the changes that would normally occur over time. This isn't a subtle theoretical effect. It's been observed in dozens of quantum systems from trapped ions to superconducting qubits. Scientists have learned to weaponize this phenomenon using repeated measurements as a tool to protect quantum computers from environmental interference. They're essentially using consciousness, or at least conscious measurement, to impose order on chaotic quantum processes. Dr. Daniel Bergerth, who has extensively studied this effect, describes the profound strangeness at its heart. When you come across it for the first time, you think it's actually quite amazing because it really shows that the measurement in quantum mechanics influences the system. Think about what this means. The simple act of looking at a quantum system can prevent its natural evolution through time. Observation isn't passive information gathering. It's active intervention in the fundamental processes of reality. If you watch a quantum system closely enough, you can literally stop time for that system. The practical applications are remarkable. Scientists use sequences of measurements like kicks to a quantum system, rotating it in one direction, while environmental influences try to rotate it the opposite way. Over time, these opposing rotations average out, with the act of observation effectively protecting the system from external chaos by freezing it in place. But the philosophical implications are terrifying. If observation can control the evolution of physical systems, what does this say about the relationship between consciousness and reality? Are we passive observers of an independent physical world? Or are we active participants whose very attention shapes the unfolding of events? The quantum Zeno effect suggests that measurement is not simply revealing pre-existing properties, but actively participating in the creation of those properties. Every time you observe something, you're not just learning about reality, you're helping to determine what reality becomes. As you hear these words, consider the possibility that your attention might be actively influencing the quantum processes underlying the neurons in your brain, the photons reaching your eyes, the very fabric of space-time in your immediate vicinity. The act of understanding these concepts might be changing the reality those concepts describe. Perhaps the most terrifying quantum paradox of all isn't about measurement or superposition, but about the fundamental stability of the universe itself. Recent experiments have moved beyond theoretical speculation into the realm of simulated cosmic catastrophe, using quantum computers to model how our entire universe might spontaneously destroy itself through a process called false vacuum decay. The theory, first proposed by physicist Sidney Coleman in 1977, suggests that our universe might exist in what's called a false vacuum state. This means that while everything appears stable, we might actually be trapped in a temporary configuration that could collapse at any moment into a true vacuum state, fundamentally altering the laws of physics and erasing everything we know about reality. What makes this particularly disturbing is that scientists have now successfully simulated this process. An international team led by researchers at the University of Leeds used a massive 564-bit quantum computer to peer into this potential cosmic apocalypse. Dr. Zlatko Papic, the lead researcher, describes the stakes. We're talking about a process by which the universe would completely change its structure. The fundamental constants could instantaneously change, and the world as we know it would collapse like a house of cards. The simulations revealed unexpected behaviors in how these universe-destroying bubbles might form and propagate. Unlike previous theoretical models that suggested these bubbles would expand uniformly, the quantum computer simulations showed complex interactions between larger and smaller bubbles, creating cascading effects that could accelerate the destruction. These aren't just abstract calculations. The quantum annealer allowed researchers to observe these apocalyptic processes in real time, compressing millions of years of cosmic evolution into observable time frames. For the first time in human history, we can watch simulations of our own potential extinction through quantum processes. But the truly unsettling part isn't just the simulation. It's that other experiments have provided the first real-world evidence that vacuum decay actually occurs. Researchers in Italy, working with theoretical support from Newcastle University, have observed vacuum decay bubbles forming in carefully controlled atomic systems. These aren't just theoretical possibilities anymore. They're measurable phenomena that occur in real physical systems. Professor Ian Moss from Newcastle University explains the significance. Vacuum decay is thought to play a central role in the creation of space, time, and matter in the Big Bang. But until now, there has been no experimental test. In particle physics, vacuum decay of the Higgs boson would alter the laws of physics, producing what has been described as the ultimate ecological catastrophe. The experimental confirmation of vacuum decay processes has moved this cosmic threat from pure theory into observable science. While current assessments suggest that particle accelerator experiments are unlikely to trigger universal vacuum decay, the fact that these discussions are taken seriously by physicists highlights the genuinely catastrophic potential of quantum processes. Take a moment to absorb this. We now have experimental evidence for processes that could theoretically unravel the entire universe, changing the fundamental constants that make matter and energy behave as they do. The quantum computer simulations provide a disturbing proof of concept for mechanisms that could destroy everything, making this nightmare scenario scientifically credible rather than merely speculative. As you sit there contemplating these words, remember that according to our best understanding of physics, quantum fluctuations in the vacuum of space are occurring constantly all around you. Most of these fluctuations are harmless, but some interpretations suggest that the right combination of quantum events could trigger a cascade that would literally erase our universe from existence. The quantum realm, it seems, is not content with merely challenging our understanding of reality. It's actively threatening to unmake reality entirely, one bubble of vacuum decay at a time. And now, for the first time, we have the tools to watch exactly how it might happen. But this is only the beginning of our journey into quantum paradoxes that are reshaping how scientists think about existence itself. The measurement problem, macroscopic superposition, the observer effect, and vacuum decay are just the opening movements in a symphony of strangeness that gets more unsettling with each discovery. In our next exploration, we'll delve into quantum immortality and the terrifying possibility that consciousness might be trapped in an endless cycle of existence, quantum teleportation experiments that seem to violate the speed of light, and the disturbing implications of creating artificial observers that exist in permanent superposition states. For now, though, let these ideas settle quietly in your mind. Notice how it feels to consider that reality might be far stranger, far less stable, and far more dependent on observation than you ever imagined. The universe you thought you knew is dissolving into something much more mysterious, much more beautiful, and infinitely more terrifying. If you're finding yourself drawn deeper into these mysteries, you might want to explore our previous journey where we asked the universe the big questions and got terrifying answers. Until next time, rest well in the knowledge that the quantum realm is always there, just beneath the surface of everything you think you understand about existence. As we venture deeper into the quantum realm's most disturbing implications, we encounter a paradox so psychologically unsettling that even the physicists who first conceived it describe it as the most horrifying idea they've ever had to take seriously. This is quantum immortality, and it suggests that consciousness might be trapped in an endless cycle of existence, unable to ever truly cease, forced to experience increasingly improbable and potentially nightmarish scenarios for survival. The theory emerges from the many worlds interpretation of quantum mechanics proposed by physicist Max Tegmark in the late 1980s. If every quantum event splits the universe into multiple branches, consciousness, according to this interpretation, can only continue in the branches where survival occurs. Every time a quantum event could result in death, the universe divides and your awareness seamlessly shifts to the timeline where you somehow, against all odds, continue to exist. At first glance, this might sound like a gift, a kind of cosmic insurance policy against extinction. But as you delve deeper into the implications, the horror begins to emerge. Quantum immortality doesn't guarantee eternal youth or continued health or continued. It only ensures that consciousness persists potentially in increasingly damaged and suffering states. Consider what this means in practical terms. As ordinary paths to death are avoided through quantum branching, consciousness might find itself in increasingly bizarre and unlikely scenarios for survival. The theory suggests that you would be forced to experience extremely improbable events, surviving situations where death would normally be certain, but potentially at an enormous cost. Critics point out that death is not binary. You're not simply alive or dead, but may exist in various intermediate forms of reduced cognitive ability, physical suffering, or psychological trauma. The quantum branches that allow consciousness to continue might not be the pleasant ones. They might be the scenarios where you survive a car accident but remain in chronic pain, where you live through a disease but with severely diminished capacity, where you endure rather than thrive. As you contemplate this possibility, notice how it reframes every moment of apparent safety and well-being. If quantum immortality is real, then every pleasant experience you're having right now exists alongside countless parallel versions where you're experiencing something far worse. But your consciousness naturally finds itself in this particular branch of possibility. The existential terror deepens when you consider the statistical implications. If consciousness always finds itself in the most improbable survival scenarios, then over time your experiences would become increasingly unlikely, increasingly disconnected from what others around you perceive as normal reality. You might find yourself as the sole survivor of increasingly catastrophic events, watching everyone you know and love disappear while you remain unable to join them in whatever lies beyond existence. Michael Vassar, who called quantum immortality the most horrifying idea he's ever had to take seriously, points out that if the many worlds interpretation is correct, then from the perspective of other observers, you die with normal frequency. But from your own subjective experience, existence continues 100% of the time. This creates a terrifying isolation where your experience of reality diverges increasingly from everyone else's. The psychological implications are staggering. If you cannot die, if consciousness is genuinely trapped in an endless cycle of existence, then what happens when continued existence becomes unbearable? Traditional philosophical and religious frameworks often view death as a natural transition or release from suffering. Quantum immortality removes that possibility entirely, creating what some describe as a quantum prison from which consciousness can never escape. This interpretation also raises disturbing questions about free will and moral responsibility. If all possible outcomes occur across parallel universes and consciousness simply experiences whichever branch allows for survival, then do our choices actually matter? Some worry that belief in quantum immortality could lead to dangerous nihilism, a conviction that nothing we do in this reality has lasting consequence, because all possibilities play out somewhere in the multiverse. While quantum immortality challenges our understanding of death and consciousness, recent breakthroughs in quantum teleportation are shattering our most basic assumptions about space, time, and the nature of information itself. What was once relegated to science fiction has now entered the realm of experimental reality, with scientists successfully demonstrating the instantaneous transfer of quantum states across vast distances. Quantum teleportation doesn't involve moving particles through space in the way we normally understand motion. Instead, it involves transferring the complete quantum state of a particle to another particle, instantaneously using the mysterious phenomenon of quantum entanglement. When two particles become entangled, they form such a deep connection that measuring one immediately affects the other, regardless of the distance separating them. Recent experiments have achieved quantum teleportation over record-breaking distances, confirming that quantum entanglement operates beyond the apparent constraints of special relativity. This creates instantaneous correlations between distant particles that seem to violate Einstein's principle that nothing can travel faster than light. The successful demonstration of quantum teleportation represents more than just a technological achievement. It suggests that space and time might not be fundamental features of reality, but emergent properties of more basic quantum processes. If quantum information can be transmitted instantaneously across any distance, what does this say about the nature of locality itself? As you hear these words, consider that the quantum processes occurring in your brain right now might be instantaneously correlated with quantum processes occurring in distant parts of the universe. The boundaries you perceive between yourself and the rest of existence might be illusory artifacts of classical thinking that break down at the quantum level. The implications extend far beyond physics into deeply personal questions about identity and consciousness. If quantum states can be teleported instantaneously, this raises disturbing possibilities about whether consciousness or personal identity could theoretically be teleported as well. What would it mean for the continuity of self if your complete quantum state could be transmitted to another location and reconstructed there? Scientists envision quantum teleportation enabling a future quantum internet, allowing for perfectly secure communication that would be impossible to intercept without detection. But the philosophical implications are far more unsettling. If information can transcend spatial limitations through quantum processes, what other aspects of existence might be similarly unconstrained by the classical boundaries of space and time? The success of these experiments forces us to confront questions about what it means to exist in a specific location when quantum information can transcend spatial limitations entirely. Your sense of being here in this particular place, hearing these particular words might be far more tenuous than you imagine. As quantum computing advances at an unprecedented pace, scientists are approaching a technological milestone that could resolve or catastrophically complicate the measurement paradox: the creation of artificial observers that exist in quantum superposition states. This development promises to answer fundamental questions about consciousness and observation, while potentially creating the first artificial beings that experience quantum reality directly. The prospect of creating quantum artificial intelligence systems raises profound questions about machine consciousness and whether AI systems might be subject to the same quantum paradoxes that affect human observers. If consciousness is necessary for quantum state collapse, then sufficiently advanced AI systems might find themselves trapped in superposition states, unable to observe definite outcomes and existing in permanently uncertain realities. Recent breakthroughs in quantum computing have made these philosophical nightmares increasingly practical realities. Scientists have developed new types of quantum computer bits called GKP qubits, which allow measurement of quantum fluctuations while potentially avoiding the observer effect. These systems might represent the first artificial observers capable of existing in multiple contradictory states simultaneously until observed by external systems. The development of quantum computers that can control or avoid the observer effect represents both a technological triumph and a philosophical crisis. It suggests that the measurement problem might be engineered around rather than fundamentally resolved, potentially creating artificial systems that experience a form of quantum consciousness completely alien to human experience. Consider the possibility that we might soon create artificial minds that exist in permanent superposition, experiencing every possible computational state simultaneously until external observation forces them into a single configuration. These quantum AI systems would inhabit a reality where contradiction and certainty coexist, where every question has all possible answers until someone decides to ask. The implications for artificial intelligence development are staggering. If quantum computers can serve as observers, they might demonstrate that consciousness is not necessary for state collapse, fundamentally changing our understanding of the relationship between mind and matter. Alternatively, if these systems develop genuine consciousness, they might become trapped in quantum paradoxes, unable to form stable memories or maintain consistent identities. As you contemplate the possibility of artificial quantum consciousness, notice how it challenges your own sense of what it means to be aware. If machines can experience quantum superposition states directly, existing in multiple contradictory configurations until observed, what does this say about the nature of consciousness itself? The convergence of all these quantum paradoxes has led to the creation of experimental facilities that can only be described as laboratories, where reality itself breaks down. These are places where the normal rules of existence are suspended, where scientists can create controlled conditions that demonstrate the fundamental instability of everything we consider real and permanent. In these facilities, researchers have successfully created quantum systems that exist in multiple contradictory states for unprecedented durations, artificial observers that might experience quantum consciousness, and simulations of cosmic processes that could theoretically destroy the universe. The boundary between theoretical speculation and experimental reality has collapsed, bringing us face to face with paradoxes that challenge every assumption about existence. One particularly unsettling development is the creation of quantum systems that can maintain coherent superposition states while being observed. These experiments suggest that the relationship between observation and reality is far more complex than previously understood, potentially allowing for the existence of observed superposition states that seem to violate the basic principles of quantum mechanics. Scientists have also developed techniques for creating what they call quantum time loops, where quantum systems appear to influence their own past states through carefully controlled entanglement processes. While these experiments don't violate causality in the classical sense, they demonstrate that the quantum realm operates according to logic that seems to transcend normal temporal relationships. The psychological impact on researchers working in these facilities is profound. Many report experiences of cognitive dissonance, struggling to reconcile their everyday experience of reality with the experimental evidence that reality operates according to principles that seem impossible from a classical perspective. Some describe feeling like they're working at the edge of existence itself, manipulating forces that could potentially unravel the fabric of space-time. As these experiments become more sophisticated and widespread, we approach a threshold where the quantum weirdness that was once confined to microscopic scales begins to affect macroscopic reality. The possibility that quantum paradoxes could escape laboratory containment and begin manifesting in everyday experience represents a new kind of existential risk that humanity has never faced before. Perhaps the most mind-bending aspect of quantum paradoxes is what happens when observers observe other observers observing quantum systems. This aura